Okay, so the central limit theorem for means. So in the previous video, we talked briefly about this. So the distribution of the sample mean approaches a normal distribution as the sample size gets larger. In other words, X bar is normally distributed with a mean of mu and a standard deviation or standard error of sigma over square root of n. Okay, so here what I wrote something a little bit more. You can use a CLT for means in the following two scenarios. If the population data is normal, then we use the central limit theorem regardless of how many samples you obtain. If the population data is not normal, so if it's skewed or something else, you need to obtain 25 or more samples to use CLT. Now, what the heck does all this mean? Okay, so let me show you a simulation. So let's pretend that our data from the very beginning is normal. So I think I did the simulation before, but I'll go ahead and do it again. So what we're going to get from our original population, we're going to get a total of 5 samples. And what I'm going to do with those 5 samples, so I grab them here, you can see that it's a sample data, and here is our parent population. So I got 5 samples and I calculated a mean. So that's in blue right here. So what I can do is I can continue getting a whole bunch of different samples, 5, and get all of their means. So I'm going to get 5 of them, get another mean, do another 5, get another mean. And I do this many different times. And if I do this 10,000 times, well, what I'm going to get is a normal distribution. Okay. Now, as n gets larger, let's say n equals 25, I can animate this. I can get 25 samples from the parent distribution. So I'm getting that, and it's taking a long time. And then I get those 25, add them together and divide by the total, and I get a mean. And if I do this over and over and over again, I get a normal distribution. Okay, so that's basically what this thing is saying. So this says that as the sample size gets larger, my sample mean is going to approach normal. The mean is going to be mu, and this is going to be my standard error. So this first one says that if I know from the very beginning that my entire, it just shouldn't say data, I should say population, but whatever. If the population is normal from the very beginning, which it is here, it's normal, then as I get more samples, I'm going to just get a normal curve. So if I first start off with a population as normal, you know, initially this is my population, my sample mean, okay, is also going to be normal. Okay, that's basically all it's saying. Now, let's say if initially my population is not, maybe it's skewed. Okay, so how is that going to affect it? So let's say, for example, now I have a skewed distribution. Well, I can let n equal a very small number, like n equals 5. I can get 5 of them, and I'm still going to get a mean. And I do this many different times. Well, what's going to happen to my data? Well, what happens is that you almost get a normal, but it's still kind of skewed. However, if I increase the number of samples, so for example, n equals 25, and I do this many different times, I'm going to get a normal curve. Okay, so basically what I'm saying here is that if the population for some reason is not normal from the very beginning, is something different, then I need to obtain 25 or more samples in order for me to use this, okay? Now, if you don't have normal data and if you have less than 25 samples, you have to do something else, okay? So you can't use the start thing. You have to use something completely different, okay? All right, so let's do a couple of problems. We're mainly going to use these two things for confidence intervals and hypothesis testing this upcoming week. Okay, so here's my first example. So the weight of cute and adorable puppies is normally distributed with a mean of 11.2 and a standard deviation of 3. I posted a PowerPoint about this one right and on Blackboard. So if you want to see a picture the cute and adorable puppies, you guys can, but I basically copy pasted from the PowerPoint. But anyways, in case you want to see the pictures. Okay, so the weight of cute and adorable puppies is normally distributed with a mean of 11.2 pounds and a standard deviation of 3. What is the probability that I select a puppy whose weight is less than 10 pounds? So there's nothing different here. There's no central limit theorem. Basically what I have is I have my normal distribution. My mean is 11.2 and my standard deviation sigma is going to be 3. Okay, so this is my mean, mu. So I want to figure out what is the probability that I select a puppy whose weight is less than 10 pounds. So, well, this is nothing new that we've done. So this is 10, everything that's less than. We know that we have to use normal CDF for this one. So this is going to be normal CDF. My lower bound in this case is going to be minus infinity. Okay, so a really, really big number. And negative number all the way to 10. So my upper bound is going to be 10. My mean, well, we know what our mean is. It's just 11.2. And my standard deviation is just going to be 3. So all we got to do in this case is just put this into our calculator. So I'm going to get normal CDF. Mean is 11.2. Standard deviation or sigma is just going to be 3. Lower bound negative infinity. Upper bound is going to be 10. And what I'm going to get is about 0.3446. Okay, so this is going to be my probability. Okay, so there was nothing that we had new that we had to do here. It's just a basic normal distribution. Okay. Now find the 75th percentile. So remember that what we're talking about here, this is going to be a really good review. Let me do it in a different color now. So this one, we want to look, okay, what is going to be my my data point if I know that 75% of the data is below it? So what is my point if I know that 75% of it is below? We know that our mean is still going to be 11.2. So what is going to be all of this data? So in order for me to do this, I need to use inverse normal. Inverse norm, my area is going to be this 0.75. My mean is going to be still 11.2, and my sigma is going to be 3. Okay, so when I use inverse normal for my calculator, area is 0.75, mean is 11.2, sigma is going to be 3. What I'm going to get is about 13.2 pounds. So a puppy who is 13.2 pounds is on the 75th percentile. Okay, now here is the new one. So suppose I got 25 puppies. What is the probability that their mean weight will be less than 10 pounds? Now, what is the difference between part C and part A? Well, in part A, I'm asking for, I am selecting a puppy who is less than 10 pounds. Here, I got 25 puppies and I want to know their mean weight. Okay, what is the probability that their mean weight will be less than 10 pounds? So here, the key word is mean weight. Okay, and remember, mean weight means X bar. So I want to find the mean weight of these 25 puppies being less than 10 pounds. Okay. Now, the question here is that now since I'm looking at X bar, this X bar is normally distributed with a mean of mu and a standard error of sigma over square root of n. Okay. Now I can only do this if my data is normal, which it is in the very beginning. So actually this one checks off. Or if I obtain more than 25 samples, which I do anyways. Okay, so this one will just, the first one would have just been sufficient. Okay, because it's already, I already know it's normal, so n doesn't really matter. Okay, so let's see. So this is going to be normal. My mean doesn't stays the same, 11.2. Sigma is going to be 3 over the square root of 25. So this is going to be normal, 11.2. And then 3 over square root of 25. That's just going to be 3 over 5, which gives me 0.6. Okay. All right. So this is going to be my new distribution. Okay. So now what I'm going to do, I'm going to graph this. My mean now is 11.2. This is going to be my new sigma. We want to figure out the probability that it's less than 10, the mean weight. So I'm still going to use normal CDF. My lower bound is still negative 1 million or whatever, all the way to 10. My mean is 11.2, and my sigma is now going to change 0.6. So this is going to be the only thing that changes. Okay, so let me use normal CDF. 11.2, now it's going to change to 0.6, negative 1 million, all the way to 10. Okay, and what I'm going to get is 0.02. Okay, that is going to be my answer. Okay, so when you're doing these types of problems, this is what you really are looking for. What mean weight? This is what you want to do, not regular weight. And I have to give you a value of n. Okay, so in the next video, I'll do another problem just like this one.